Start, sir.
Yeah, good afternoon, and anyone present here to our live query session. In this NPTEL course on scanning electron ion probe microscopy in material characterization, I have discussed some of the important microscopic technique that includes scanning electron microscope, which is extensively used in examining the surface morphology of the material, the shape, size, and that also provides us elemental composition if we have energy dispersive X-ray detector attached with the system. First, after discussing the scanning electron microscopy, that is most commonly and extensively used by the scientist and also the researcher, then we went to discuss on helium ion microscope. That is quite new. There are not many helium ion microscope around the world, including in our country. So, not much has been there in the literature on the helium ion microscope. I have covered whatever the information available until date on helium ion microscope, which is in many ways superior to scanning electron microscope, particularly in terms of resolution and also in terms of depth of field. Helium ion microscope is better. It is because we have seen that one of the demerits in the scanning electron microscope to achieve high resolution is the aberration. So there are three aberrations. One is the spherical aberration, other is chromatic aberration, and the diffraction aberration. So there was one question on the spherical aberration last time in our forum question. So there was a formula on spherical aberration DS, which one time I mentioned it is 2 CS alpha Q, which is CS is the coefficient of spherical aberration and alpha is the angle of aperture. So this 2 CS alpha Q is used when we are in the image plane. On the other hand, we use half CS alpha Q on the plane of least confusion, disc of least plane of least confusion. So both the formula are correct, and just the value one case half, other case 2. Otherwise, the spherical aberration coefficient C and 3 power of angle of aperture remains, other parts remain same. So in addition to that, two other, as I said, two other aberration are there. One is chromatic aberration, that is also directly proportional to the alpha. Alpha is the angle of aperture. And we have diffraction aberration, which is directly proportional to the lambda. Lambda is the wavelength. So if wavelength of incident rays can be small, then diffraction aberration can be small. And diffraction aberration formula is 1.22 lambda divided by alpha. So if lambda, or nothing but the wavelength of incident electron or ion, can be small, we can have a smaller diffraction aberration. So then, if we have a smaller diffraction aberration, we have a liberty to use a smaller angle of aperture because that is in the denominator. So as we can use the smaller angle of aperture in case of helium ion microscope, our spherical aberration and chromatic aberration will automatically be small. And therefore, in the helium ion microscope, such type of aberration correction is not necessary. And in helium ion microscope, this angle of aperture is around 100 microradians, which is around 10 to 100 times smaller than that used in the electron microscope, scanning electron microscope or electron beam tube. So therefore, Helium ion microscope is providing us high resolution. When I say high resolution, means it is around 0.3 nanometer as compared to around or greater than 0.5 nanometer for scanning electron microscope or FESE, field emission scanning electron microscope. In addition to that, as I said, because we can have a smaller angle of aperture alpha, our depth of field will be large. So if the sample surface is quite rough or inhomogeneous, then also we can get a much focused image of the surface through the whole range of the image. This is the advantage of helium ion microscope. Moreover, for helium ion microscope study, it is not necessary to coat or to coat the sample with a conductive layer. Without a conductive layer also, we can have a much improved or better quality image with the helium ion microscopy. So these are some of the advantages of helium ion microscopy, which has come in recent years. Recent years means last 10, 12 years that has come to the market, which is not yet that popularized, like the scanning electron microscope, which almost every university and institute have. Some of the institute have several of such scanning electron microscope, unlike the helium ion microscope. Then we have also discussed on energy dispersive X-ray analysis, mostly attached with scanning electron microscope, used for elemental composition analysis, except the low atomic number elements such as hydrogen, helium, lithium, beryllium. Boron onwards, we can detect and quantitatively say approximately how much percentage of such element are present in the sample by measuring the energy of the X-rays that come out of the sample. So in the SEM, as we have seen, electron beam incident on the sample, and when it incident on the sample, it can remove some of the inertial electron. So once it removes an inertial electron, it produces a vacancy, and that vacancy is filled by an electron from the outer shell. So when an outer shell electron comes to the inner shell electron to fill that vacancy, it releases energy in the form of X-rays, X-ray photon. So by knowing the energy of that X-ray photon, we would be able to tell what element present in the sample, because every atom in the periodic table has different electronic configuration, and the energy level difference of inner cell and outer cells are different. So by knowing the X-ray energy, we can tell what type of element present in the sample and how much proportion of the element present in the sample. In addition, we have also seen in scanning electron microscope, backscattered electrons are also utilized to differentiate the higher atomic number element atom and also lower atomic number element. So if, for example, I have probably given an example, nickel incorporated to alumina. So nickel with higher atomic number element has a higher backscattered electron yield as compared to lower atomic number elements such as aluminum and oxygen. So more number of backscattered electrons will come out of the sample if a higher atomic number element is present. So from the contrast difference, we would be able to say which region has higher atomic number element and which region has lower atomic number elements from the contrast difference. Knowing the distributions of different components, particularly if their atomic numbers are different, we would be able to tell it. So this also we can do in scanning electron microscope. So after so these two, examining the surface morphology and elemental composition, are primarily studied by the scanning electron microscope. As the field emission scanning electron microscope have resolution, the modern field emission have a resolution of less than 1 nanometer, we can see the features of size less than 1 nanometer without any problem. So that's all nanomaterial research is confirmed. The synthesis of the nanomaterials or their shape and size are first primarily confirmed by the field emission SEM. before going for any other analysis, because it is quick and exclusively do not need a very tedious sample preparation. If the sample is metallic in nature, then you do not need also a conductive coating. You can put the sample in the, it can be powder form, it can be thin film form. If it is a powder form, you can mount it on a carbon tape, or you can disperse it on a solvent, and such as alcohol solvent, and then disperse the solvent to a aluminum foil, and then put it under microscope to study its morphological properties. This is what normally done to study. If you bulk sample, you can certainly directly take it. Sample as large as 10 centimeter can be taken inside the microscope. It depends on the model of the microscope, how big its chamber size. So that is not an issue. But in conventionally, in most cases, it is being preferred that sample size be less than 1 centimeter by 1 centimeter. Then once inside the, when you take the sample for microscopy studies, such as SEM, etc., you need to know what parameters to change. The major parameters that will vary is the acceleration voltage. Acceleration voltage normally in the scanning electron microscope, it is varied between 1 kilovolt to around 20 kilovolt. The microscope allows us to go up to 30 kilovolt, but up to 20 kilovolt is good enough to study. And if the sample is soft or biological sample, polymeric sample, then it is preferred that we use lower acceleration voltage. To get high resolution image, an acceleration voltage of approximately 1 to 2 kilovolt or less than 5 kilovolt is good enough. So higher acceleration voltage is not required for soft sample or low atomic number samples, because the maximum secondary electron yields is around 2 to 5 kilo electron volts of acceleration voltage. And other parameters that we vary is the working distance. So working distance can be varied, and if we want to see the sample in a larger area, then we should prefer a little larger working distance. Otherwise, if we want high resolution image, then a smaller working distance is preferred. Because at a smaller working distance, we can have a probe diameter very small. So in this way, and also if, for the energy dispersive X-ray analysis, the acceleration voltage should be greater than 50 kilovolt, because the amount of X-ray generated at a lower acceleration voltage is small. So in order to increase the X-ray yield, we should use a higher acceleration voltage. That means it should be greater than 50 kilovolt at least. So 15 kilovolt to 25 kilovolt can be used for energy dispersive X-ray analysis study. Moreover, another important features, as I have discussed, why helium ion microscope gives better resolution. Not only that of it has a smaller wavelength because of higher mass of the helium ion, but also the generation of secondary electrons. So more number of, there are two types of signal generated. One is SC1 and SC2, both in scanning electron microscope and helium ion microscope. And also there is SC3, depending upon from where these electrons are emerged, we term as SC1, SC2, SC3. For example, when incident beam hits on the sample, and from there itself, secondary electrons are emerged, that we term as SC1. And on the other hand, when a backscatter electrons come out, and from that region of the sample, when a low energy electrons comes out, those are called SC2. And when the backscatter electron strikes to the chamber wall or the wall piece, and then lower energy electrons comes out, those are termed as SC3. It all depends on from where those electrons emerged. Moreover, as you might be remembering, you might have remembered that the energy of the secondary electrons is less than 50 electron volts. On the other hand, energy of the backscatter electrons is greater than 50 electron volts. So any electrons coming from the sample or another area of the chamber, if the energy is less than 50 electron volt, we say it is a secondary electrons. On the other hand, if energy is greater than 50 electron volts, we say it is extra electrons. So as I said that SC1 comes from the region where the primary incident electron beam or ion beam incident on the sample. So those gives the best resolution. And in scanning electron microscope in FESCM or SCM, the yield of SC2 is higher than SC1. So relatively, the area from which SC2 emerged is a little larger as compared to the region or area from which SC1 or volume from which SC1 comes out. As SC1 comes out from a smaller area, a smaller volume from the region where electron beam strikes, so therefore that gives best resolution. And SC1 yield in that is that ion-induced secondary electron yield in helium ion microscope is much higher as compared to the scanning electron microscope. That is another region for which helium ion microscope give better resolution as compared to the SCM scanning electron microscope. For example, one ion beam incident on the sample surface will produce more than approximately 3 to 8 SC1, which is much larger than FESCM case. On the other hand, in FESCM or SCM, the yield of SC2 is larger. So this is one reason, another reason why helium ion microscope give better resolution. So after discussing scanning electron microscope and helium ion microscope, we move to another scanning microscopic technique that is called scanning probe microscopic techniques. So here the scanning, well, in all cases it is the scanning microscopic technique. That means something scans over the sample surface. First cases electron beam scans on the surface, that is SCM. Then in helium ion microscopic cases, helium ion scans on the surface. And in the scanning probe technique, again, a probe scans on the surface. Unlike the electron beam or helium ion beam scans on the sample surface, here a physical probe scans on the surface. That is called scanning probe technique. And under scanning probe, under the umbrella of scanning probe techniques, there are several techniques available, including the scanning tunneling microscope, atomic force microscope, and we have also discussed a number of force microscopic techniques, including that like a magnetic force microscope, chemical force microscope, electrostatic force microscope, and shear modulation force microscope, etc. etc. There are several scanning probe microscopic techniques we have covered, but most commonly atomic force microscope and scanning tunneling microscope are used by the scientific community. First is scanning tunneling microscope we have discussed. Scanning tunneling microscope involves measuring the tunneling current flow between the sample and the tip. And depending upon the current measured between the tip and sample, we could get a three-dimensional image of the sample surface. Particularly because here tunneling current is measured, so the sample has to be conducting. So we apply a bias potential. Upon applying the bias potential, when the tip means it is a probe, when coming close to the sample surface and there is a bias, the current, and there will be current can tunnel, electrons can tunnel from sample to the tip or tip to sample, depending upon the type of bias applied. And that tunneling current depends exponentially with the distance between the tip and sample. So when tip and sample distance varies 1 angstrom, then tunneling current will vary 10 times. So when the tip or probe come close to the sample 1 angstrom, the current will increase 10 times. So that gives us a very high vertical resolution. Remember, now I am talking about the vertical resolution. That means height difference. Previously in the scanning electron microscope and helium ion microscope, we talked about lateral resolution. in the horizontal scale, lateral resolution. So lateral resolution of scanning electron microscope is around 0.5 nanometer, helium ion microscope 0.3 nanometer. So in the same sense, scanning probe microscope with scanning tunneling microscope, you have a resolution, lateral resolution of about 0.1 nanometer. So better than scanning electron microscope and helium ion microscope. So the resolution is much higher or better in scanning tunneling microscope, because here atomically sharp tip is used. So what the probe has only a single atoms at its tip or apex. Therefore, current pass via a single atom. So when single atom moves, one angstrom moves laterally, 1 angstrom, it could see another current. And like that, as different, we can map the current over the surface at a particular area of the surface, and we could measure, we could get the resolution as good as 0.1 nanometer laterally. But in vertical, even we can get better resolution. That is 0.01 nanometer, like 0.1 angstrom. So, for example, if you have a monolayer of graphene, graphene is placed on a flat surface, and another is bilayer of graphene. When you if your probe is scanning at a constant height, then what you will see? You will see a more current when it comes to a region where bilayer of graphene is there, because constant height over the surface. So bilayer means it has a little higher height, and therefore the distance between the probe and the sample is closer. Therefore, you get much higher current compared to when the distance or gap between the probe and surface is large. So we can, from as the current varies exponentially, we would be able to measure the vertical height in a range of 0.1 angstrom, the vertical resolution. So this vertical resolution quantitatively, or vertical height quantitatively, we cannot measure by scanning electron microscope or helium ion microscope. That we can do with scanning probe microscopic technique, both with STM and AFM. Here, remember, so in previous cases, our electron beam probe diameter was important. Here also probe diameter is important. There it was the electron beam size. On the other hand, here is the physical probe, the diameter of the tip. This is the difference. So, moreover, in previous cases, as electron beam has a charge, electron is a charged particle, therefore scanning on the surface can be very fast. We can use electrostatic lens to scan very quickly on the surface. On the other hand, in scanning probe microscopic technique, we cannot scan very fast, because here a physical probe has to move step by steps, and therefore it is not as fast as the electrostatic scanning process. So scanning probe microscopic technique is a slower technique. Moreover, we cannot do it on a large area, because there are several reasons it cannot be done with a large area that I have discussed in my lectures, like particularly when the tip or probe moves, that we use piezoelectric scanner, and piezoelectric scanner have a certain voltage range. It will move to a certain distance, certain XY direction, and if we apply a larger voltage to the scanner, then the non-linearity, hysteresis, creep, all those effects come into picture. Therefore, both STM, scanning tunneling microscopy, and atomic force microscopy do not allow us to scan on a larger area that we can do in helium ion microscope and scanning electron microscope. So this is, and another requirement of scanning tunneling microscopy is that sample must be conducting, because here we measure tunneling current. Because we measure here tunneling current. So if the sample is not conducting, then we cannot measure the current. Therefore, we cannot create a image of the sample surface. Moreover, It's here electrons tunnel from the tip to sample or sample to tip. We can get density of states or electronic properties of the sample. So by applying a negative bias to the tip, we can know the unoccupied states of the sample. On the other hand, by biasing uh, positive to the tip, we can know the field states of the sample. So that we can do by scanning tunneling microscope, and that therefore those are also utilized to know how the electron occupancy around the atom, how electron density occupies around its atom. Some region whether there is no electron clouds, and some region there is electron clouds. So the density of states, electronic properties of the surface can be measured by scanning tunneling microscope that we cannot do by atomic force microscope or by SEM or helium microscope. So this kind of technique cannot give. But in all cases, remember, in all cases, in all these microscopic technique that we have discussed, we get the surface information, not the bulk information. Surface information means how the surface is how the surface is either the surface features of the sample can be measured by these techniques. Again, as I said, that STM requires only conducting sample. On the other hand, AFM, atomic force microscope, can be used to study insulating sample. So insulating samples, for insulating sample, a force between the sample and tip can be measured to know that which places there is a strong force, which places is a weak force. By measuring or mapping the force across the sample surface, we can create an image, and that would be three-dimensional image. For example, in the atomic force microscope, as we know, there is a cantilever and there is a tip. So if the probe or tip come close to the surface, close to a feature in the sample, there will be attractive force. And if there is a little and they come much closer to the sample, there will be repulsive force. So there we have different type of force exist, and by measuring the force, and that force we can measure by the amount of bending in the cantilever. So if there is a stronger attractive force, cantilever will bend more downward, and how much it bends, using that bending amount, we could able to tell how much force exists at that particular location between the probe and sample, and that force can be used for creating a three-dimensional image. If we want, in other hand, we can also keep the force constant and make the tip or probe move. So, for example, we want the force between the sample and tip to be always, let's say, 1 nanonewton. And then my tip should go up and down to locate, to measure, to see that force of 1 nanonewton. If somewhere there is a pit or there is a hole, so my tip will go inside the hole much closer to find a surface. Tip will go downwards and see a 1 nanonewton force, and then as my tip or probe go downwards, I would know how much it goes downwards. Accordingly, my 3D image will be created where those region will be shown as a pit, or because tip has gone downwards. In that process, we can create a three-dimensional image. So AFM can be used for both conductor and insulators, first things. And also, I have also discussed that AFM can also be utilized for phase imaging, like knowing the surface stiffness, elasticity, adhesion, because all those are different type of force exist. We have different type of sample have different type of force, like there can be capillary force, a magnetic sample have magnetic force, and depending on the type of force exist on the sample surface, one can measure those force and then measure those properties of the sample surface. For example, you have a sample surface where some region are magnetic in nature and other region are not magnetic in nature. Then when the tip, in that cases, the probe has to be magnetic in nature. When probe moves from non-magnetic region to magnetic region, it will experience a magnetic force. And then that magnetic force can be utilized to uh, create the image and be presented which region has magnetic portion of the magnetic portion in the sample and which region does not have. In this way, we can study different type of forces in the atomic force microscope. So, particularly these atomic force microscope, scanning electron microscope, are extensively used for research purpose and also for knowing the certain information depending on what information one is looking after. Uh, what information is looking after. And so far, I do not see any question, and I would be happy if there is some questions. Please feel free to write your questions. Hello.
Sir.
I think no one is writing any questions.
Yes, sir. No question.
So we can stop here, or we should
Yes, sir.
continue?
You can, sir. You can.
Okay, then we can stop here if they have no question. Or certainly, you are also free to write by email any questions.
Yes.
So either myself or my TAs will answer those questions.
Yes, sir. Yes, sir. No problem. So you can close from your end.
I will call.